pair of lights connected in parallel here, and they're being fed by two single wire conductors from some category 5 cable. The category 5 cable generally has 4 pairs of conducting wires. These 3 pairs here are currently not being used. I'm only using 1 pair of the small single strand conducting wires. The voltage that I'm measuring here on the digital multimeter across the lamps is 23.1 volts. And that 23.1 volts we're going to find is lower than the starting voltage at the beginning of the cable. I'll go back into the classroom where the power supply is, we'll follow the cable back to the classroom, and then we'll find out that we start with 24 volts. And the question becomes, where does that 900 millivolts of voltage drop originate from? So there's our lamps, nothing like a park bench seat to put the lamps on. Here's our category 5 cable, following it back into the classroom. We have 16 metres of category 5 cable being employed in this lab. The 16 metres terminates in a power supply, and if we put the multimeter into the power supply, I think I've mentioned before, never rely on what the power supply readout says. It's going to be in the ballpark, but it's nowhere near as accurate as even the cheapest DMM. DMM is a much more precision instrument to use for measuring voltage. So the DMM tells us that we've got exactly 24 volts. Now we know then that we do in fact have 900 millivolts of voltage drop in our system. We have 24 volts starting from the power supply, and then right outside the classroom, out in the corridor, we only have 23.1 volts. I've modified where the cables come from the power supply unit now, and I've used a second pair of wires which has been tied in parallel with the first pair of wires. There's a good reason for doing this. It allows me to remotely monitor the voltage from the power supply. It'll give me the terminal voltage at the power supply from a remote location. And how is that possible? It's possible because the only load on that other pair of wires will be a digital multimeter with 10 million ohms of internal resistance at the far end. Here we have the remote end again with the 2 bulbs, and now I have 2 meters employed. I have the first meter showing me that I've got 24 volts, and it's been connected up next to the, it's been connected up in parallel with the blue and white pair of cables. So as I said inside, the meter itself has 10 million ohms of internal resistance, so therefore the amount of current that the meter is drawing is very, very small, and there's effectively no load across that cable, so the voltage that we're getting here will be identical to the terminal voltage on the power supply itself. Now I'm going to go ahead and I'm going to put another load resistor in parallel with our lamps, but before I do that, we'll just again check. We've still got our 23.1 volts with the lamps, and now I'll go ahead and I'll put across the lamps. So here's our resistor, putting it across the lamps, and you can see the lamps dull. I'll do that again. You can see the lamps dull. The voltage at the source has not changed, but the voltage across the lamps now has dropped from 23 volts down to 21.5 volts, and that resistor is getting very, very hot. So the extra load drew so much more current, and we'll run the calculations on that, that we were getting that extra voltage loss in the cable. Now, we can overcome that voltage drop by utilising the other pairs of copper wire. If these were put in parallel back to the power supply and then put across the load, we would increase the cross-sectional area of our conducting wires to the load, and therefore we could minimise that voltage drop in the cable. Maybe we'll go ahead and try that. So now I'm back at the voltage source again, the power supply, and I've put all 4 pairs of wire together. so that we're really maximise the use of the copper wire that we have available. However, one pair is being used for remote monitoring on the DMM, and 3 pairs are in parallel supplying the lamps and the resistor, which I'll ultimately put across the lamps again. So let's go back to the remote point and see how that's going. Okay, back at the remote point, we've got all of the pairs connected. As we said, we've got 3 pairs connected in parallel supplying the load, and we've got the blue and white pair as previous, just supplying the meter for remote monitoring. So we've got 24 volts supplying the circuit again with just 2 lamps, and now instead of 23.1 volts we've got 23.7. We've only lost 300 millivolts instead of 900 millivolts because we've added extra copper wire. We've got more conductors, larger cross-sectional area, and therefore we've reduced the resistance in the cable. Now I'm going to go ahead and put that back across the load, and that really drew some current previously, and we lost something like 3 volts across the copper wire. So let's go ahead and put that on. It gets hot fairly quickly. The thing I notice now when I put it on, it's not dimming the lights. That's the first thing I noticed. It is reducing the voltage though, just a tiny bit. We're going from 23.7 down to 23.1. So now we've picked up almost 2 volts by stranding those other parallel conductors together. And as I said, that gets quite hot in a very, very short amount of time. That's almost too hot to hold that now. We'll run the power calculations on that shortly. There we are again, remote monitoring, our loads, and the voltage across the load.